Thank you all very much for joining this Performance Tech Talk today. I'm Brad Chen, and it's a pleasure to introduce Amir Dewan from the University of Colorado, although he seems to know more people here than me, so I'm not sure I should waste too much time of his time since it's his talk. But yeah, very good. So Amir, please take it away.
Thanks a lot, Brad, and thanks all for coming. So I'm going to talk about work that I've been doing with my students and colleagues at University of Colorado and one colleague at IBM Research. Now, before we start most work in experimental systems, one of the first steps that we do is to identify bottlenecks. So for example, let's suppose we want to improve commute times in an area. And so what we might do is we might give out a number of surveys to drivers, and we ask them that at the beginning of the commute, they should record, or at the beginning of each segment of the commute, they should record the starting time, do the commute, and when the commute ends, they should record the end time. And since we collect data from a number of drivers, hopefully our data is representative of what really happens. Now, the next step that we often do after finding bottlenecks is that we act on the data. And in this particular case, we might realize that maybe we should build a bridge across this lake and thus avoid this bend, which is particularly slow for the commute. Now, this bridge allows you, hopefully, to do your commute faster. But what if the data is wrong? What if we have identified the wrong bottleneck? In that case, we end up with a bridge that nobody needs. Now, how could the data possibly be wrong? Let's suppose this is what happens in reality when no one is measuring anything. So you do your commute, and then after the rush hour ends, there is a train that's scheduled to go across the road. Now, when you actually do the observations, the collection of the data delays the commuters ever so slightly, so that now, rather than finishing their commutes before the train comes, they get to the train tracks, they have to wait for the train to pass, and then they finish their commute. A consequence of this is that this commute looks a lot slower than it would have if you were not observing the commuters. This is an example of a phenomena that's known as the observer effect, and it comes about because the act of observing a system might change the system. Now, this particular study, it's an easy study to conduct. We gave out a number of surveys and then left it up to the individual drivers, to the individual commuters, to fill out the forms and to use their stopwatches. However, it's not a right survey because it changed the data. Now, if you look at this a bit more abstractly, this red block here represents the prefix of the commute until you get to the train tracks. We can move this prefix around as long as you don't get to the train tracks while the train is still there. It is not a problem. But if you move it so that you get to the train tracks while the train is there, you suffer a significant delay, and thus your commute time is much longer. Now, so far I've been talking about trains, and you're probably wondering if you've come to the wrong talk. Well, not really. Let's think about computer systems. And instead of a commute prefix, imagine this red block is a hot object. The object might be a data object, or it might be a code object. And this barrier here, this wall, represents a page boundary. Just as with the commute, I can move this object around, but at one point, I will end up straddling the page boundary. So rather than fitting on one page, I now fit this object on 2 pages. And when that happens, your program will probably run much slower because you have additional paging activity. Now, why do objects move around when you collect data? Imagine this is our program, and this is an important loop. And this here gives the memory addresses of the various parts of the program. Now, in order to collect data, at the very least, you need to add a little bit of instrumentation at the beginning of the program to initialize your data collection. And then you may need to add some more instrumentation at the end of the program to record the data that you collected. Now, what has happened is that as a consequence of adding this instrumentation, we have shifted code around. And because we have shifted code around, as we saw in the previous slide, a hot loop that used to fit on a single page might now fit on 2 pages. So in this slide, I'm going to show you that this phenomena actually happens in practice. I'm presenting the data for just one benchmark in this graph, and then I'll show you all the other programs that I have used. And what we are doing in this case is that we are collecting data using hardware performance monitors. So hardware performance monitors are perhaps the cheapest way to collect data from a computer system because the hardware does all the hard work of doing the increments. All you have to do, as I showed you on the previous slide, might be to initialize the counters at the beginning and then read them out when you need their values. Along the x-axis, as you go to the right, we collect more and more hardware performance monitors. On this particular machine, you can collect up to 18 monitors at the same time. And so all of these can be collected simultaneously by the hardware. The y-axis gives us the ratio of the execution time when you collect only one metric, which is cycles, divided by when you collect n metrics, where n is the number on the x-axis. The thing that is surprising to note for this program is that going from 1 metric to 2 metric can actually speed things up by about 7%. And going from 2 to 3 can actually slow things down by about 7%. In other words, the shifting of the code as a result of collecting hardware metrics significantly and actually chaotically changes the performance of this application. Yes, please.
I thought the whole point of hardware counters is that you don't have to modify the code.
You don't have to modify the code to do any incrementation of the counters, but you still need to initialize the counters and read out their values at some point. Okay? So this is data for just one program, and now I'm showing you data for the entire spec int 2006 benchmark suite. So these numbers identify programs. Now, the interesting thing to note here is that for some programs, adding counters can degrade performance, improve performance, and for others, it actually degrades. And these 2 programs are the most extreme. So this one sees a change in nearly 20% as a result of collecting data. But if you eliminate these 2 programs, there's still quite a lot of variation along the order of 3 or 4% for these other programs. In other words, the insignificant overhead of collecting hardware performance monitors can also change data. This is not intuitive. This is not what you would expect. Now, in this graph, I'm showing you not hardware metrics, but software metrics. Now, software metrics, as you would expect, are more work. And so to collect software metrics, we need to go and modify the program to increment counters. So for each of these programs, we identified up to 100 different events that could be interesting for performance analysis. And for each event, whenever it happens, we increment a counter for that event. So for example, if this is a database application, then at the end, you might know how many times each transaction happened. So there's one of these violins for each benchmark program. And the y-axis gives you the execution time when you collect no software metrics divided by the execution time when you do collect software metrics. Now, this is a lot of data, so we summarize the data using these violins. The violin plot is a very powerful plot. It can capture quite a few things in a very compact picture, so let me explain it to you. If you look at a violin sideways, it basically gives you a histogram. So it gives you a distribution of values. So for example, this fat area here indicates that we see about a 5% change in performance for a majority of the time, and then there's this tail that extends on either end. The white point in the middle gives you the median that we observed. Each violin represents the data for collecting 1 software metric, 2 software metric, 3 software metric, all the way up to 100 software metrics. The interesting thing to observe is that these violins are incredibly tall. So for example, this violin extends from about 1 to 0.82. In other words, we are seeing an 18% swing in performance as a result of collecting software metrics. Now, you might wonder, if we have added a lot of instrumentation to collect the software metrics, then we expect a big change in performance. Well, it actually turns out that that's not the case here. The numbers above the x-axis tell you how many instructions we added dynamically for collecting our data. So the most extreme case is about 2%. In other words, all the increments that we added to collect software metrics changed the instruction count, dynamic instruction count, by up to 2%, and oftentimes by much less. The thing to observe here is that the big swing in execution time we see is disproportionate to the instruction count that we have added. So in other words, a very, very small change in the instruction count causes a big change in performance. So we cannot expect that if our instruction overhead is small, our observer effect is small. It may actually be huge. Now, where does this observer effect come from? What happens is that when you add instrumentation, it pushes code or data through some boundary. And unfortunately, these boundaries are everywhere in a computer system. For example, you might push it from one cache block to a different cache block. You might exceed the cache size. You might go over a page boundary. You might go over a TLB, and so on and so forth. So these boundaries are everywhere in the computer system. And by moving things around, who knows which boundary you're going to push things over. Unfortunately, this is not the worst of the problem. The worst of the problem is yet to come. So let's continue with our commute example. And now that we have built our bridge, we want to ask, is this bridge a good idea? Was it effective in doing what we intended it to do? And so you might devise a study where you ask your coworkers. And your coworker might say, I can get to my office in half the time. And from that, you might draw broad conclusions like, hey, the bridge cuts my commute in half. Now, if you believe that study, then perhaps I can sell you yet another bridge. The problem with that study is that it's easy to do. I just polled a bunch of my coworkers. But it's not right. It's wrong. And the reason why it's wrong is that it's potentially biased. Your coworkers may not represent the entire population of commuters. And in the context of a computer system, your experimental setup on which you do your experiments may not represent the whole population of experimental setups. And so, if you do your experiments in one or a few setups, you might end up heavily biasing your results. You might end up with results that are biased towards your setup. And this particular phenomena is called measurement bias. Now, does this actually arise in practice? For this set of experiments, what we are doing is that we are comparing two things, much like we were talking about comparing a commute without the bridge and a commute with the bridge. And the two things we picked, just for interest, is the performance of the code produced by GCC's O2 optimization level versus GCC's O3 optimization level. So the y-axis gives you this ratio. And the way this ratio is, if you see numbers above 1, it means O3 is beneficial over O2. And if you see numbers below 1, you see that O3 performs worse than O2. As before, we have one violin for each benchmark program. The first most interesting, and what I'm doing in this case to change my experimental setup is that I'm changing environment variables. So these are Unix environment variables. And what we did is we created a dummy variable, and that variable has nothing to do with your program. And all we are doing is that changing its size. Now what that does is that the environment variables show up under the, or over the, depending on how you look at it, over the stack, the execution runtime stack of the program. And so changing the environment variables shifts the stack around. And doing this completely innocuous thing, so we change it from 0 to 4096 bytes, we see huge swings in performance. And worse, for 4 of the programs, their violins straddle 1.0. In other words, depending on the environment variable you happen to pick, you might conclude that O3 is beneficial, or you might conclude that O3 degrades performance. So you come to completely contradictory conclusions. Now, this has significant consequence. So for example, let's suppose I set up an experiment on my machine, and I run it. And then I ask a colleague to run the same experiment on my machine. If that person has slightly different environment, they may get very different results. And indeed, we tried that, and that's what happens. Okay? So the setting of irrelevant environment variables leads to contradictory conclusions. It ends up biasing the result one way or the other. Here's another instantiation of that. The graph follows the same format. And what I've done in this graph is I've changed the link order. So the order of the .o files to the Unix LD linker. So I've just reordered them. There's nothing else that I have done. Once again, as you can imagine, changing the link order changes code layout, and of course you end up with interactions with the memory and other subsystems of the computer. And we see for 32 randomly generated link orders, each violin summarizes the data we got for one benchmark program. We see that these violins are huge. By changing the link order, we can change the performance of these applications by close to 20%. Okay? And many of these violins straddle 1.0. In other words, not only do you come to a different conclusion about the magnitude of the speed up, but you might come to completely contradictory conclusions. You might think that it's beneficial, but it's not, depending on the link order that you picked. Now, I don't show you that data here, but you might ask, what if we pick the link order that the makefile has for these programs? And we actually tried that. The default link order, which is what's specified in the spec makefiles, or the alphabetical link order, neither of them are the best link order. In other words, you can speed up your program potentially by up to 20% by just moving the link order around and seeing what happens. Now, where did this measurement bias come from? So as I mentioned, the environment variables in link order, they affect code and data layout. And of course, these are not the only sources of measurement bias. There are many other sources of measurement bias. So for example, some of them are domain independent. So to give you an example, the temperature in the room may affect whether your machine favors compute-bound applications versus memory-bound applications. But unfortunately, along with the domain-independent sources of bias, there are also domain-dependent sources of bias. So for example, the heap size for a garbage collected system, people now know that depending on the heap size you pick, you may come to completely contradictory conclusions about which garbage collector is the better garbage collector. So there are so many sources of measurement bias, domain-dependent and independent, that it's not something we can easily suppress. Now, the next thing to ask is measurement bias predictable? If it's predictable, then maybe we can get around it somehow. So what this does is that it takes the violin for one of the benchmarks, Perl bench, and it gives you all the points that lie within that violin. And the data for the other benchmarks are similar, so I omit that. And the x-axis gives you the environment size. So basically the size of this dummy environment variable. And the y-axis gives you the execution time of O2 over O3, so the ratio that we have been looking at all along. The thing to note here is that adding an environment variable can make O3 look better, such as here it looks 7% better than O2. Or it can make it look much worse, and here it looks about 9% worse than O2. So adding environment variables does not have an easily discernible, predictable behavior. We cannot predict this behavior and act on it. Now, what about different architectures? So if, for example, we picked one link order on one architecture, and we picked the best link order on that architecture by trying all the possible link orders, would it give us the best link order on another architecture? So here along the x-axis, I give you the execution time for a Pentium 4 workstation. And along the y-axis, I give you the execution time for a Core 2 workstation. And we produced these binaries so that we could run them unchanged on both the machines. So it's the exact same binary on both the machines. And each point represents one link order. The point here that I have circled, because it's the lowest point along the y-axis, gives us the best link order for the Core 2 machine. The point here, because it's the leftmost point along the x-axis, gives us the best link order for the Pentium 4 machine. In other words, the best link order for one machine may not be the best link order for another machine. So you cannot just pick one link order which performs the best in your environment and expect the results to carry over to other environments. Now, we have so far used GCC for all of our experiments. And you might be wondering if this behavior is an artifact of GCC. In particular, since we are using Intel machines, if you use an Intel compiler, maybe the Intel compiler designers are smarter, and maybe they'll know how to do things right for that machine. And so in these graphs, I present data for the link orders for the Intel compiler, not GCC. And once again, we see huge swings in performance. In other words, this phenomena is not an artifact of something that GCC does. Intel's C compiler suffers from exactly the same phenomena. Now, are these phenomena caused by a poor methodology that we might have followed? Actually, we followed the best methodology we could find or come up with. We used the Spec CPU 2006 C benchmarks, and we used train inputs because they're already quite long, and we needed to run tens of thousands of runs. We used the best practices. So we tweaked our instrumentation so it was as lightweight as we could come up with it. We ran our experiments on lightly loaded machines, used only local disk. There was no network activity, etc. We did 15 runs for each experiment. So even though I haven't shown it on the graphs earlier, actually I have shown it, but you might have missed it. We computed confidence intervals for every run. So we have 15 runs for each experiment, and the confidence intervals are very, very tight. And the reason why you haven't noticed is that the error bars are so tight that they're almost invisible. And we reproduced these experiments on 4 different architectures and 2 compilers. So we conclude that we actually followed as good a practice as one could follow. Now, in the past, when I have talked about these phenomena, I've talked about, you move code or data and it hits some barrier and it interacts poorly with it. But I haven't told you what barrier it hits. And it actually turns out that to figure that out is incredibly difficult. We have figured a few of those things out, but in general, it is incredibly difficult. In particular, to figure out what exactly is happening in the underlying machine, you need 2 things. First of all, you need to have a deep knowledge of what that computer hardware actually does. And you need to be able to collect data from the computer hardware that allows you to test your hypothesis. Unfortunately, hardware designers do not reveal many details of their hardware. And there are many things you would like to collect that they don't allow you to collect. So to give you a brief example, for some of the phenomena that I've showed you, one of the culprits might be the loop stream detector, which detects loops and latches them into the instruction queue. But unfortunately, because Intel does not reveal all details about the algorithm that the LSD uses, we can't confirm that that's actually what's happening. Also, Intel does not make available metrics that measure what the LSD is doing in an execution. So we can't see what it's actually doing. Yeah, I'll leave it at that. So we can guess what is happening, but it will be very, very hard to pinpoint the exact underlying causes. Now, how do we, as computer scientists, deal with these issues? So in order to get a sense for that, we surveyed papers from top systems conferences, including ASPLOS, PACT, PLDI, and CGO. And we looked at all the papers in 2007 for these 3 conferences. And for ASPLOS, we looked at 2008. There was no ASPLOS in 2007, so we couldn't do that. And of the 133 papers we looked at, 88 papers had an evaluation section. So potentially, those are papers that might suffer from the phenomena that I'm describing. And so then we asked the question, for those 88 papers, what do they do with observer effect and with measurement bias? Now, 36 of those papers used simulations. The great thing about simulations is that you can avoid the observer effect. Because with a simulator, you can add things so that you don't end up causing an observer effect. Unfortunately, you might still suffer from measurement bias. So what we did in this graph is that we took the M5 simulator, which is one of the most prominent public domain architectural simulators out there from Michigan, and we use its accurate O3 CPU model, and we tried many different link orders. So we did the same link order experiment that I described earlier, and the x-axis gives you the normalized speed up, or the speed up that we got of O3 against O2. And the y-axis tells you how many times you observed a particular speed up. So in some sense, this is a histogram that gives you a distribution of the results. We see that even in the simulator, if you take the rightmost point and the leftmost point, we saw almost a 20% swing in performance due to changing link orders. In other words, simulators may be immune to observer effect, but they are not immune to measurement bias. It's something you still have to deal with. Now, of the 88 papers that had an evaluation section, 83 papers used more than one workload. Now, the idea there is that if you have a diverse workload, if you have many different things in your workload, and you compute averages, it may be that for one benchmark, you may be biased in this way. For another benchmark, you might be biased in that way. And you hope that if you have a large enough workload set, then the biases will cancel each other out. So you report average numbers. So what we did here is, in this graph, I'm showing you numbers that are averaged over all the spec int 2006 programs plus the 3 C programs in spec FP 2006. So it's 12 benchmarks. And the x-axis gives you the speed up, but this is the speed up that is an average over the entire benchmark suite. If it was the case that the benchmark suite was large enough to cancel out bias, then we would see a very tight distribution. Instead, we see a broad distribution that spans about 7%. In other words, it could be that if you use enough programs, it will cancel out bias, but at least the 12 standard benchmarks that we used were not enough to cancel out bias. Now that we have looked at what CS systems researchers do, we should look at what other sciences do. These phenomena, of course, are not specific to computer science. Other sciences have dealt with them for hundreds of years. There's basically 2 techniques that other sciences follow. The first technique is that they use many different measurement setups. And then they use statistical techniques, such as the t-tests, to derive conclusions from the many different measurement setups. And the hope, again, is that by using a diverse enough set of measurement setups, your bias will cancel itself out. The second thing that they do is causality analysis. The main idea behind causality analysis is that you're not trying to get correct data. As a matter of fact, you recognize that correct data is impossible to get in general. But what you are trying to do is to determine if the conclusions you have drawn from the data are correct, even if the data itself may be tainted. So I'll demonstrate how we have been using these techniques by giving you 2 examples. So for the many measurement setups, we do setup randomization. So rather than collecting data, for example, using just one environment variable setting and one link order, we collect data with many different experimental setups, and then we draw the distributions. So in these violins, these points here, the circles, they represent what you get if you collect data in only one measurement setup. So this is what we saw in the past. And the x-axis adds hardware metrics. So this is going back to our adding one hardware metric at a time example. And these violins show the distribution that we get. And the interesting thing is that if we compare these distributions, they're nearly identical, even though the individual points are quite far apart from each other. So here, these 2 points are like 12 or 13% apart. And so by looking at these distributions, we can conclude that it's unlikely that the hardware data collection is actually affecting performance. It was just an outcome of the observer effect or measurement bias. So we compared these distributions using t-tests. Now, this particular technique is popular in the social sciences, right? So for example, when they go out to poll who's going to be the next presidential who's going to be the next president, they don't go to just one small town and ask them because that's going to be biased. Instead, they go to lots of different diverse communities and try to extract information from there. And that's exactly what we're trying to do here. But of course, the difficulty with this approach is it's not perfect. And as a matter of fact, there's numerous examples in social sciences and in medical sciences where they encountered exactly the same problem. And the problem is that the effectiveness depends on how representative your setups are. If despite the fact that you try many setups, if your setups are not representative, then you cannot draw any broad conclusions. Causality analysis works as follows. The first thing that you do is you analyze the data to arrive at some hypothesis. Now remember, this data might be tainted. It might be affected by the observer effect. So for example, you might come to this causal chain. So this causal chain says that when you change the size of the environment, it causes a change in the address of the stack, which in turn changes performance. So let's suppose this is our hypothesis. So the next step of causal analysis is to perform an intervention. In other words, you find a link in your causal chain and you break that link. So in this case, we broke this link. And the way we broke this link is by adding a directive that made sure that the stack always started at the same address, no matter what size of environment variables we used. And so if with this intervention we expect that now changing the environment variables should have no effect on performance. And that's what we have to check. Now it actually turns out that for most programs, this hypothesis was the correct hypothesis. For one program, this hypothesis was not the correct hypothesis. So this rejected the hypothesis, and then we had to come up with another hypothesis, which we were then able to validate. And of course, I'm happy to talk about that if you're interested in that. So you can ask if you like. All right. All right. So this approach is popular in the sciences, but it's a very, very difficult approach to do, because to come up with a link that you can break is entirely non-trivial. It's not so easy to break this link without also affecting lots of other things. Now, I'm going to conclude with a call to action, things that we should try to do as a community. The first thing is that I think in a lot of computer systems research, we have been giving a strong preference to new algorithms over insightful evaluations. And we need to recognize that to actually do an insightful evaluation that really explains some phenomena correctly is just as hard as coming up with yet another new algorithm. And so we need to recognize that by a cultural change, we should reward careful experimentation. The second is we need better workloads. Well, okay, I need better workloads at Google. You probably don't need better workloads. But one of the issues that I demonstrated is that at least the benchmarks that we used, they were not diverse enough to cancel out measurement bias. So we need workloads that are more diverse. We need more information on microprocessors. And Sun, not too long ago, open sourced one of his Spark designs. And that's great, because now if I have a question on how its loop stream detector or whatever it has works, I can look it up. It might be painful, but at least I have a way of looking it up. But with Intel, when it does not release details, there's nothing that I can do, at least in academia. And finally, we need much better hardware support. We need to have data for all the key components. So for example, in the Core 2, there's a new feature called the loop stream detector that is heavily advertised, but there is no detail that Intel reveals on exactly how this thing works. And we cannot actually, there are no hardware metrics that are available to me with which I can measure that particular component. Also, it would be nice to have a mapping from hardware events to software events. And this is also starting to appear in microprocessors. So for example, the precise event-based sampling allows you to do some of that, but it only does it for a handful of metrics. It'd be nice if you could do it for everything. So what are the key lessons from this talk? First of all, just because you have a small amount of instrumentation does not mean you have a small observer effect. I hope I've convinced you that changing things by an insignificant amount can have a huge observer effect. Second, observer effect and measurement bias, they're unpredictable. We can't tell if adding one more environment variable will make it better or worse. They're commonplace. We have seen this in all the programs we have tried and on four architectures, one of which was a simulated one. And it's large enough to obfuscate data. I mean, a lot of, in our literature survey, we found that the average speed up that papers reported was around 9%. Given that we are seeing 20% swings due to changing link orders, how do you trust your 9% speed up? Now finally, other experimental sciences, they have expended a lot of effort to work around these phenomena. And we have ignored most of those techniques. We've had it easy, but I think we haven't had it right. We have been collecting data that doesn't make sense necessarily. Now, I will conclude with an enumeration of some of the other things that I work on, in case anybody has interest in talking to me about that. So I have a number of projects that have to do with optimizations. There's blind optimizations, where you're trying to optimize things without actually understanding what the microprocessor does for exploiting hardware features. There's a project on algorithmic optimizations where we use both. There's actually two systems, one a compile time system and one a runtime system for finding opportunities to improve performance at an algorithmic level. We are also doing a lot of work on using techniques from nonlinear dynamics. So computer systems are nonlinear systems, and they're actually turns out to be they're chaotic systems. And so we're using techniques from that domain for validating simulators and for understanding the performance of computer systems. And I also have interest in software engineering, where we are working on an improvement to refactoring called program metamorphosis. And I'll stop here and take any questions. Neil?
So for the measurement bias, unlike the other sciences, we have the benefit that we can actually fix the problem in the sense that you gave a link order example. That seems to be another avenue for optimization. Same with stack alignment and so on and so forth. So when you say that we should try many different experimental setups, part of that involves knowing the problems that you want to reproduce. And it seems like if that's half the battle, that if we knew the problems, there'd be some project somewhere working on factoring that out, so we always pick the best one for that particular axis of change. So do you have any suggestions for how we actually identify these things that are causing the biases?
That's a good question. And basically, the answer to that is that I don't, but I don't feel bad about it because the sciences that have been doing it for hundreds of years don't either. This is a very, very difficult problem. So to give you an example, I read a medical study which what it did was it looked at 49 papers that were in the top medical journals, and they were each heavily cited. So they each had at least 1,000 citations. And they found that later studies that used more diverse populations and larger populations found that a third of those studies were, 13% of the studies were actually incorrect. And then there was another 13 or so percent that were found to have made exaggerated claims. And the reason for those things was that the initial studies had ignored a particular confounding variable. And that confounding variable is what we have to find, basically. So I think I don't have a quick answer to this. And the answer is that if we as a community start to value these kinds of things, then as a community we will discover over time many of these things that we can either use to do better evaluation or, as you say, better optimization.
Yeah, I really viewed most of your slides as rather than being disappointing as jotting down new projects that somebody ought to be working on.
Great, excellent.
If there's a 20% swing, that's great.
That is awesome, right, that's awesome.
So regarding that, I have a couple of comments. So the link order, you can use the L order to order the object files in specific orders using the topological sort of
Sorry, I'm not hearing you too well.
There's a utility called L order, which will order your list of object files according to the topological sort of the symbol dependencies. And then there are other compilers and tools that will reorder at the function boundaries or even the basic block boundaries.
Sure.
So those will control that variable, which will reduce the variance. Because it's been common that whenever you have uncontrolled aspects, like, for example, the alignment or things like that, once you start controlling it, the variance tends to get reduced. So
I think you're being very optimistic. Yeah. And the reason for that is, and optimism is good, but I think that the reason for this is that these computer systems are just mind-numbingly complex. Okay?
Yes.
So you're doing your link or you're reordering stuff. You say, okay, I'm going to make sure every loop starts on a 16-byte alignment. Okay, but maybe it's not the particular loop, it's something inside the loop. So the issue is that there are so many different hardware structures, and you have to kind of play well with every one of them in order to squeeze the best performance out of it, that I think any kind of static technique, it's going to be unrealistic, I think.
No, what I'm saying is I'm not saying you will eliminate all the variances.
Right.
But as you control more and more, you will have reduced the range of the variance. Because it's typically when you have totally uncontrolled stuff, you will see random scatter all over the place. Sure. And once you start controlling it, you will see reduced range.
Right, but if you control every single aspect of your experiment,
you can't, right?
there will be no variation whatsoever.
Right.
Which is the whole point of doing the experiment, is to actually discover something.
Right. Right, but to discover something, you want to control it. That's what I'm saying. As you found more problems, you should control. And without just letting it go, you should control it more.
But as
more.
I showed, right, the link order that works well on one microprocessor does not work well on another microprocessor.
Right.
So you do your experiments on your workstation, controlling everything.
Right.
And then you tell your friends, or write in your paper that I controlled, I fixed this link order, I used this basic block ordering, I used this environment variables, but they're using a slightly different microprocessor. They're not going to be able to reproduce your results.
Right. But as a practitioner, what we care about is we know exact platform we are going to deploy, exact processor. We can control this stuff. So we want to find all the best combinations that we can get the best performance out of.
Right.
So we want to find out all those controllable stuff, and we want to control it, right?
Yeah. Okay, he was using 32 different link orders, which would be a handful of modules, 5 modules.
Yeah.
How many modules do we have in a typical Google application?
Even the object level link order is still random because the real issues is much finer grain, right? So even if you control that level, it's still there's random stuff. So you want to control more and more.
See, the thing is,
as Neil said, it's an optimization.
If you know exactly what environment you're going to run on, and you have plenty of patience, then there are searches that you can do, some kind of hill climbing to try to find a good link order.
Right.
But if anything changes, in your environment. So for example, you're dynamically linking to a library, and somebody installs a slightly newer version of the library that's 2 bytes bigger or 2 bytes smaller, all bets are off. So it's...
No, all bets are not off. So
I'm going
okay.
to suggest you guys maybe have lunch together.
Sure.
Obviously, very interesting topic.
And before I go away, so my final comment is the address shift and the performance approximation is my favorite interview question, and you just blew it away. So I'm going to have to find another question.
Actually, are there other questions?
So what happens if you combine two variables, so link order and environment variables?
They have a larger effect than individual, but it's not predictable or additive.
But so we see up to 20%.
Yeah.
So it stays up to 20%?
No, it goes higher than that, but it's not additive. So,
No,
for example,
I understand it's not additive, but how much higher?
So we've seen up to 30, 35%. It goes very high.
Because if there is one variable we can easily change, we can try to optimize it for one
You're absolutely
configuration, and hope for the best. I mean, we'll need to calibrate every time we change a bit, but it may be worthwhile.
You're absolutely right.
Other questions? Okay, I had one question for you, Amir. I think if you look over the last 20 years, one could argue that computer systems are getting more susceptible to this effect. I mean, 25 years ago, we were running on 7.8 VAX 11 780s. They barely had a cache. Instructions retired in a single cycle. So I think repeatability was maybe less of a problem. And so over that time frame, repeatability or these kinds of issues perhaps have become worse. I'm wondering if you accept that assertion, and if you do, then whether you're in the literature you surveyed, have you seen any improvement in methodology, or are we all just irresponsible?
All right. So let me answer both parts. I think your intuition is probably okay that things have become more complex now, and so these problems are more common, but the math doesn't necessarily bear that out. So in particular, as I mentioned, we have been using nonlinear dynamics from chaos theory, and we are finding that even when we simulate really old, outdated machines, even they exhibit chaotic behavior. So now it's kind of like a spitting contest. Were you more chaotic than I am, right? Or is the current machine? So in some sense, even they had the potential to have these wild and crazy things. But intuitively, you're probably right that maybe it was a less frequent event. In terms of methodological improvements, I mean, when you and I were in graduate school, right, there was a lot of papers out there that were just appalling. For example, they would simulate the number of cache misses, and they say, oh, each cache miss costs 6 cycles, and we multiply it out, and we get something useful out of it. And I think around the time that we were doing this stuff, we had already started to realize that that was simply not going to work, because each cache miss has a very, very different cost, and each TLB miss has a very different cost. So I think that things have improved in that people are not making linear assumptions. So people are at least acknowledging that computer systems are not linear. But I think that there are some of these things which we still don't take care of. And obviously, you can't really fault us. We are young science compared to the other sciences that actually do know how to deal with this.
Variance is a problem. Wouldn't it be good to say that hardware manufacturers should, as an aim, not just have to make things as fast as possible, but also to narrow the range of efficiencies you can get?
Yeah, that's an excellent point. I was talking to this.
Repeat the question. Sorry, repeat the question.
Oh, right. So the question is that if this variation is such a problem, shouldn't hardware manufacturers try to build machines that are more predictable? Or, yeah. So you're absolutely right. And I was talking to this great engineer at Intel just last week. And what he confirms the phenomena that we were seeing, and what he told us was that what they are trying to do is, you know what, the methodology I described where you run many setups, they're doing things similar to that, but they're not doing it to get measurements. They're doing this on future generation hardware. So they have a simulator for future generation hardware, and they try all of these things. And if they see wild and crazy stuff, then they try to say, hey, let's identify the particular feature and let's tweak it so that it doesn't give that behavior. Even historically, you see phenomena like that that we have seen, right? So for example, the Pentium 4 has the infamous trace cache, which I think almost anybody who's used that machine for performance analysis realizes that it makes a mountain out of a molehill. I mean, a little change, you end up with trashing the trace cache or not. And as we see that the trace cache has largely disappeared from Intel's own microprocessors. And at one point when the Pentium 4 was out, I was asking Intel engineers, so how in the world do you do any performance evaluation on a Pentium 4? And they says, we don't use a Pentium 4. So I think that this is one of those things that has been biting them also, and they're trying to deal with it. But I think the bottom line is that I think it's a bit naive to expect that we can eliminate these things. We might be able to reduce the likelihood, but we will not eliminate it, because these computer systems, they are nonlinear, they are chaotic, and they are going to exhibit these nonlinearities if we tickle them in just the right way or just the wrong way.
One last question.
Okay. So I've worked on IE64 in the past, and IE64 has a...
Sorry, there's a lot of background noise.
Yep, sorry. So I've worked on IE64 in the past, and IE64 has a very complex performance counters, 325 events on the McKinley chips.
Yeah.
So the problem there was that people don't, or it's very hard to find out what those events actually measure.
Yeah.
So even if you do get the measurements, you still don't understand exactly what they do and what they mean.
Exactly.
So even if Intel were to give us better instrumentation into all of the components that you have, I'm wondering how accessible those still would be. Right?
That is an outstanding question. And I think that to look at that, one should look at the Power 4, for example. IBM does a much better job of sort of documenting their hardware performance monitors and explaining them. And you're absolutely right. I mean, just giving you, if you have ever looked at those performance counters and you look at their names, they mean nothing, right? And so you're absolutely right. Not only do they have to give you the counters, but they have to tell you what they actually mean. You're absolutely right.
Let's thank Amir.
Thanks a lot.